Alright, this is the second video on how concentration affects the rate or the speed of a reaction. And in this one, we're going to take a look at an example problem where we relate a rate law to the effect of concentration on rate. So how does this rate law affect what the concentrations of these are on the speed of the actual reaction? So here we have a made-up reaction, A plus B goes to C, and here is its rate law. Rate equals K, A to the first power, B to the second power. Rank the reaction mixtures below from the slowest to the fastest. So I'll give you a second to write these down. Here are three different mixtures of concentrations of A and concentrations of B. And I'm going to move this out of the way and I'll zoom in on it a little bit better so then we can kind of just focus on the problem. So remember, the rate expression, also known as the rate law expression, sometimes just known as the rate law, tells you that the speed of the reaction is equal to a unit called K, which is called the rate constant, remember it's a small letter K, times the concentration of one reactant to a certain power called an order, times the concentration of the second reactant to a power that's called an order. And so for this one, this would be second order in B, first order in A, and then overall third order reaction. Now, to find out which ones are going to give us the fastest rate, we would just take these concentrations and we would plug them into this rate expression. Find out what the number is, and the bigger the number, well, that's the faster the rate. So for mixture number one, we would take and put it into this equation right here. Rate is equal to K times 5 for A, 5 for B, and then square it. And that would end up being 5 times 25, or 125K. So we don't know what K is, but as long as K is the same, because it's the same for every reaction, they don't tell us that the temperature changes, then we can just know that it'd be 125 times whatever K is for this reaction right here. So then for mixture 2, we'd take the 7 and put it in here for an A and raise that to the first power. The 3, put it in here for B, raise that to the second power. 3 times 3 is 9, times 7 is 63, so we'd have 63K. So obviously this one's going to be faster than this one. And then the last one, we'd take these numbers, so we'd put 3 in for A, 7 in for B, and raise that to the second power. So 7 times 7 is 49 times 3, that'd give us 147K. And this one would be our fastest reaction rate then. And so when we're ranking them from the slowest to the fastest, our slowest would be number 2, 63. Our middle would be 125, and then our fastest would be the 147K. So the rate of a reaction is obviously affected by the initial concentrations of those reactants, but they can be very changed by what K is. And so we did it by saying K stays the same in this reaction, but the rate constant is many times the quantity of interest if you're comparing different reactions to know if it's going to be really fast or not. So if K is really big, like 10 to the 9th or bigger, then you know the reaction is going to be really fast. If K is like less than 10, well, then you know it's going to be a really slow reaction. So those are like just, possible areas. But knowing what K is, the value, and knowing its units are super interesting for reactions. So the units of K, the units of K depend on the rate law or the rate expression. Is this first power, is this second power, is this third? Is this third power, first power, second power? It always depends on that. So for the next couple of example problems, we're going to calculate the overall order of a reaction. I'm going to give you 3 reaction rate expressions, and then we're going to determine the units of K for at least 2 of them. So I'm going to move this one out of the way. I'm going to slide this one over so I've got some room to work, and then I'm going to give you a second to copy down these reactions. But here are 3 example rate expressions or rate laws. The first one, rate equals K N2O5 to the first power. The second one, rate equals K H2 to the first power, I2 to the first power. And the last one is rate equals K CH3 to the first power, Cl2 to the 1/2 power. Ooh, a real odd one there. And then for all of these, we're going to assume that rate, this rate right here, is measured in molarity per second, concentration per unit time. That'll help us find the units for K. So we'll go through each one of these and we'll calculate those pieces. First of all, the overall order of the reaction, remember, you take the exponents and you add them together. This one only has one exponent, and since nothing's written there, it's a 1, so that overall reaction order is 1. And so for letter A, for a 1, it would be 1. For letter B, determine the units of K. Now we have to do some unit analysis for this. For rate, it would be molarity per second, because it tells us molarity per second per rate. K are the set of units we want to know. We don't know what that is. And then N2O5, remember when it's in brackets like this, it means concentration or molarity. So it would be times molarity right here. Now we want to get K alone by itself to find out what units would be left for K, so we would divide both sides by capital M. Divide both sides by capital M. The M's right here would cancel, the M's over here would cancel, and the only thing we're left with is K is equal to 1 over seconds, or the other way that it can be written is seconds to the negative 1. All right, example number 2. For this rate expression, calculate the overall order. Well, this is to the first power, and this is to the first power. Add those two together. Overall order is 2. Determine the units of K. All right, rate, remember, is measured in molarity per seconds. K, of course, is the thing we want to find the units for. H2, well, that's going to be molarity. And I2, that's going to be molarity as well. All right, so we've got to get K by itself, so we'll divide this side of the equation by molarity squared, because that'll cancel these guys out. And whatever we do to this side of the equation, we also have to do to this side of the equation, so I'll have to divide this side by molarity squared as well. So these guys cancel. This one's going to cancel, but only one of these will cancel right here. So for K, the units are going to end up being 1 over molarity times seconds, or the fancy way to write this would be molarity negative 1, seconds negative 1. That'd be the fancy way to write it instead of writing 1 over like that. All right, for reaction number 3, whoops, letter A, what is the overall order? 1 plus a half. Okay, 1 1/2. That's our overall order. B, find the units. Rate is molarity per seconds. K, that's what we're looking for. This would be regular molarity. And then this would be molarity to the 1/2 power. All right, we want to get K alone by itself, so we're going to have to divide this side by molarity and divide it by molarity to the 1/2 power, or I could say I'd divide it by molarity to the 3/2 power. That would be okay as well. Now whatever I do to this side, I also have to do to this side, so that means I have to divide it by molarity and by molarity to the 1/2 power. These guys all cancel. This cancels with this, and K is then equal to 1 over molarity to the 1/2 power times seconds, or the fancy way to write this is molarity to the negative 1/2 times seconds to the negative 1. All right, that's 2 example problems using the rate law expression. First of all, finding out by concentration which would be the fastest, and then second of all, manipulating rate laws to find out what the overall order is and to determine the rate constant K.